podcast is brought to you by LMU Munich.
I'd like to thank the organizers for organizing this wonderful conference in this really quite spectacular lecture hall here. And I'm going to talk today about some recent progress in a subject which is now about 10 years old. So de Sitter space is appearing at the forefront of both theoretical and experimental physics. Of course, most recently, in the last 10 years, it's been discovered that there's a positive cosmological constant which suggests that the very far future of our universe will be de Sitter space. Theoretically, de Sitter space is also puzzling, but the puzzle begins right at the very beginning, and that is, what exactly is it that we want to understand about de Sitter space that we don't? What is the question? And I would like to advocate here that an interesting question to ask about de Sitter space is to try to find the microscopic origin of the formula that the entropy of de Sitter space is a quarter the area of its event horizon in Planck units. Now, this is really kind of an incredible equation, because if you look at it, on the left-hand side, is statistical mechanics, and on the right-hand side, we have geometry, which is gravity, and the formula becomes divergent when quantum effects are turned off, so it also is divided by quantum mechanics. So this simple formula, which contains a very definite numerical factor, relates three of the main areas of modern physics, and moreover, it does so in a way, the best part about it is it does so in a way which we really don't understand very well. And so that really gives us a lot of very interesting things to try to do and to try to think about. Now, of course, it's very similar to the formula. It's really the same formula and should ultimately be derived in the same way as the formula for the entropy of a black hole. And we've made a lot of progress. It would be too much to say we've solved the problem, but we've certainly had some significant insights into understanding the black hole analog of this formula, using what we've learned from string theory and various investigations in quantum gravity and so on. And so this problem appears to be of the general type that we can solve doing the kinds of things that we've been doing for the last 10 or 20 years, using the tools and ideas that we have at hand, and we don't need to wait for an experiment to help us solve this problem. Indeed, it's hard to think of what experiment would help us to unravel this puzzle. And one thing that is so deeply vexing about it is, in the case of a black hole, at least there was a place where the microstates could live. Somehow, if we had a dual description of the black hole, we could count quantum microstates, take their logarithm, and reproduce this entropy formula. In de Sitter space, the location of the horizon depends on the observer, so it's not even clear where the microstates should be. And so I'd like to say that the existence of such a well-posed, deep question about the ideas that we are investigating bodes very well for our field. I won't answer it. Now, there are many other ways, other kinds of questions about de Sitter space that get raised. And I'm putting these in a secondary status because most of these people, there isn't even a general agreement on what the question is and whether or not it has been answered. And I think as time goes on, as we understand the subject better, it will be clearer which of these are the right questions and which aren't. The first question is, what are the physical observables in de Sitter space? So we've long been used to the idea that the S matrix is the physical observable in Minkowski space, even in quantum gravity in asymptotically Minkowski space. We've more recently come to the idea that in asymptotically anti-de Sitter space, the observables is the set of boundary correlation functions appropriately rescaled. And I'd like to point out that that idea that is the set of observables in anti-de Sitter space probably, I don't know the history so well, but probably emerged with recent developments of the ADS CFT correspondence. If you had asked somebody in the 80s what are the observables in anti-de Sitter space, they would likely have said something about evolving initial data with boundary conditions to some other kind of final configuration. And so our understanding of the inner workings and the details of anti-de Sitter space have worked hand in hand with stating what the correct observables are in anti-de Sitter space. Some people have been so bothered by the puzzles of de Sitter space that they've concluded that eternal de Sitter space can't exist at all, that it's a self-contradictory entity. There's also been the proposal that it exists, but it somehow has a finite number of states, unlike most quantum systems, which have infinitely many states. Now, when we study anti-de Sitter space or Minkowski space, we don't just study the exact spaces themselves. We consider a more general family at the same time of spaces with the same asymptotics. And indeed, our own universe is plausibly a geometry which is asymptotically de Sitter in the far future, but certainly is not exactly de Sitter everywhere, certainly is not de Sitter as we speak. And in such near de Sitter universes, there's a classical theorem of Guth and Vilenkin that as you go backward in time, under some generic circumstances, the matter will concentrate and there'll be some kind of Big Bang, suggesting that there's a beginning of time. And if there's a beginning of time, the question raises, is there such a thing as unitarity in de Sitter space? What do we mean by unitarity in de Sitter space? And what do we mean by unitary in quantum gravity in general? So about 10 years ago, a tool was proposed to address these questions, the DSC FD correspondence, and it was suggested by the rather striking and simple mathematical relationship between de Sitter space and anti-de Sitter space, and it seemed very natural to try to capitalize on the successes of anti-de Sitter space and adapt them to de Sitter space. So how does that go? Let me just remind you how this goes. Well, here's four-dimensional anti-de Sitter space, and here is what's often called the Poincare patch, and the Poincare patch is covered by this metric, and the boundary is when this coordinate eta is 0, and everything expands the Minkowskian slices. These slices are each Minkowski space, and they expand as you go to the boundary. Now there's and in ADS CFT, there's a dual formulation of the bulk physics in anti-de Sitter space, which lives at this boundary at infinity. Now, this boundary doesn't actually have a metric on it. The metric is going to infinity there, but it has a conformal metric. It has a metric which is defined up to local conformal transformations. So any kind of structure, the only kind of structure that could sensibly live on this boundary would be, which we call the holographic plate, is a conformal field theory. Now, to get from here to here, you just do a triple analytic continuation. You take the anti-de Sitter length and multiply it by I. You Wick rotate this spatial coordinate eta into a time-like coordinate, and you also take one of the space-like coordinates on these three-dimensional Minkowski slices and make it time-like, and then all of a sudden you have a de Sitter space which looks very similar, and we see that the holographic plate, which lived here at spatial infinity, where the conformal boundary is, has moved up to time-like infinity. And so even though there's a great mathematical similarity here, of course, conceptually it's very different to have a holographic plate that lives at a moment of time rather than at a moment of space. There's also huge physical differences. In anti-de Sitter space, the measurements made at the boundary by one experimentalist can be communicated causally to another experimentalist. But up here in de Sitter space, all the points on the boundary are space-like separated, and therefore no communication is possible. So the objects that are defined up here cannot be understood in terms of, or numbers that exist up here cannot be understood in terms of causally related experiments. Now, I want to concentrate on this region of de Sitter space, which is the region that exists in standard cosmological FRW coordinates. And if you perturb de Sitter space, you tend to get a singularity, and this second region tends to disappear. So if you add some matter, an asymptotically four-dimensional de Sitter space will tend to have some kind of big bang in the past. Similarly, in anti-de Sitter space, if you add a relevant perturbation, you lose the global so that it's no longer exactly conformally invariant. If it's only conformally invariant in the UV, then if you add a relevant perturbation which produces a mass gap, you'll find that if you move in the radial direction, the space-time comes to an end in one form or another. And we see that this picture here is this picture turned on its side, so that the Big Bang in de Sitter space should somehow be related to, or the de Sitter analog of the creation of a mass gap in anti-de Sitter space. Ashok, what time did I start? I started 12 minutes ago? Okay. So what is DSC FD? Well, DSC FD is an adaptation of the minimal form of ADS CFT. So in ADS CFT, we say that we have some field theory which lives, conformal field theory which lives on the holographic plate, and it has some set of correlation functions, and those correlation functions are equal to the correlation functions of the bulk theory pushed to the boundary with appropriate boundary conditions and rescaled by some factor of the distance to the boundary. Now, ADS CFT is really more than that. You can you can put a finitely deformed metric on the boundary, and we've done a lot more non-perturbative things with ADS CFT than just look at relationships between correlation functions. But this is sort of the minimal form of ADS CFT, and we should try to get the DS version of that before getting to the more non-perturbative analogs. So the DSC FD conjecture is that if you have a bulk theory in de Sitter space, that you could take the points of the Green's function, push them to the boundary, and rescale them, and what's left is defined by the correlation functions, or is reproduced by the correlation functions of some conformal field theory which lives on the boundary. And just from looking at the solution of the wave equation, just as in anti-de Sitter space, we learn that these eta factors, these rescaling factors, have to correspond to these conformal weights. There's a similar formula that can be derived from the wave equation in de Sitter space. Now, I want to emphasize that this is not a complete proposal for a physical theory. If I want to make a complete proposal for a physical theory, I also have to make some statements about what the observables are, how we interpret these objects, and so on. In other words, I have to provide some kinds of answers to those questions on my second transparency. And I will comment on some of those questions as we go on, but I want to emphasize that what we're doing here is really just to get the kind of building blocks of a theory of de Sitter space, which we can then hopefully try to put together to get some kind of physical interpretation. Now, some quick comments. One is that these conformal weights are in general complex, so the CFT can't be unitary, but it must have some good property that we don't quite know how to characterize. And in fact, even at the classical level, it's hard to say. The unitarity of the conformal field theories that are dual to anti-de Sitter bulk theories ultimately follows from is the quantum analog of the positive energy theory in asymptotically ADS gravity. And we don't have a positive energy theorem in de Sitter space. There's something called cosmic boldness and other kinds of conjectured properties, but we don't even know what the classical property is whose quantum version we would like to preserve in such a theory. Another feature is that since the holographic plate is time-like and the holographically emergent direction becomes time, that means the time evolution becomes renormalization group flow. And though the mathematics seems to push us in this direction, it's really a rather radical assertion because renormalization group flow is dissipative and seems at odds with the idea that time evolution should have a unitary character. And becomes even more vexing if you think about trying to take some DSC FT, some CFT which is dual to de Sitter space, and perturbing it so that there's a mass gap, and then you have an energy scale at which there's no more degrees of freedom at all, and that means in the bulk boundary dictionary, that means that there's a time before which nothing existed, so-called Big Bang. And also I want to say that the relationship to the area law I put on the first, the first transparency is not understood. So this is all, I've gone through this quickly because this is all old. And there have been many papers written on this from many different points of view. And there have been a lot of interesting structural properties of DSCFT that one can deduce just from consistencies and the property of quantum gravity. There have also been some useful applications to using it as a way to characterize CMB physics and its deviations. But there have also remained there have been many inconclusive discussions, and there have been a lot of unanswered questions. And the reason for that is that we're not very good at things when we don't have concrete examples. So all the discussion begins with the statement, had begun with the statement, if we had an example of DSCFT, this is what it would have to do by consistency. And that we tend to get lost when we venture down that avenue. Now, many people have tried, and I still think it could be possible, but many people have tried to get a simple, stable, de Sitter solution of string theory that we could control enough to answer these kinds of questions. And as much as string theory loves anti-de Sitter space, it seems to hate de Sitter space. So the new progress is that there's a different theory of quantum gravity that has been discussed recently a lot, and of course it's very old, the Vasilyev higher spin gravity, which is equally comfortable in de Sitter and anti-de Sitter space, as was noticed in the very earliest papers on the subject. If you take lambda goes to minus lambda, you find that de Sitter space becomes anti-de Sitter space, and moreover, all the conformal weights are unchanged under this transformation, and so and in particular, there are no imaginary conformal weights in Vasilyev gravity, and so in particular, they're all real. So, what has happened in the last year is that this Vasilyev gravity has been used to construct a nearly soluble example of the DSC FD correspondence. Now, tomorrow she is giving an overview of higher spin gravity, so I'm going to give an overview of the overview because I have to use it. So the basic idea is that you have a bulk theory in ADS4 where you have a bunch of higher spin fields, and on the boundary you have an ON model which is holographically dual to it in the usual ADS sense, and there's two flavors of the conformal field theory on the boundary. It's an ON model, either the critical one with the Wilson-Fisher fixed point or the free ON model. And there are also two bulk theories with two different boundary conditions for the scalar field, Dirichlet-Neumann, and these pairs of things are dual to one another, and there's an important formula here that actually depends on the numerical factor, depends on your conventions, but n goes like 1 over h bar times Newton's constant times the cosmological constant lambda, and there's been all kinds of beautiful work on this over the last several years, all of which I think we should be able to adapt to this de Sitter context. So what happens if you take lambda to minus lambda in this duality? We've known for 30 years that we could easily transform Vasilyev gravity and anti-de Sitter to de Sitter. Well, I'm making something seem a little simpler than it is. To really work through this, you have to look at the reality conditions for the Vasilyev master field and look at how the equations of motion transform and so on. But in the end, it boils down to this. When you take lambda to minus lambda, you want to keep h bar and g Newton fixed to keep local positivity of the energy of the fields. And that means you take n to minus n, and so On goes to O minus n, but O minus n, as I'll explain on the next transparency, is actually the same thing as the SPN model. So the example of DSC FD then is Vasilyev DS4 gravity, and with two possible boundary conditions in the SPN model, the free or the critical version. Now, wait, sorry. Why is ON SP minus N? Well, why is O minus N SPN? Well, the SPN model is like the ON model, but made with anti-commuting scalars. And if you work it through, there's a simple diagrammatic explanation that every time you get a loop with a factor of n, the anti-commuting bosons give you a minus sign. And so the SPN correlators for singlets are equal to the ON ones with n replaced by minus n. And this was discussed some time ago in a completely different context by Leclerc and Neubert. So the summary is that all the evidence for the ON ADS the ON Vasilyev correspondence can be analytically continued to a DS SBN correspondence. And so now we have, at least mathematically, an example of the DSC FD correspondence. So in the two remaining transparencies, I want to talk about what we can do with it. Well, one interesting thing is it reveals, so now we should try to understand this, develop the dictionary, see what it tells us about physics in de Sitter space. And if we take the scalar field operator and we look near scribe plus, there are two fall-off behaviors, and each of these operators is dual to an operator that lives in the conformal field theory on scribe plus. But this operator acting on scribe plus, if we take it at the North Pole, creates what's called a quasi-normal mode for the southern diamond. And the quasi-normal modes form a complete basis in de Sitter space. On the other hand, using the DSC FD dictionary, we can write this operator, the bulk field operator rescaled near scribe plus, as an operator in the dual field theory. And we see here that since it's constructed from anti-commusing bosons, if we raise it, of which there are only n, if we raise it to some large power, we get 0. So this tells us that there's a kind of de Sitter exclusion principle. Ordinarily, if you take a mode and a boson, you can put as many bosons as you want in that mode. But here we see that there's a limit on the number. It's non-perturbative. It's going like 1 over h bar. N is going like 1 over h bar. So already we're getting some glimpse into the non-perturbative structure of de Sitter space described by this DSC correspondence. And possibly this is related to the finite number of states in de Sitter space. And then finally, I want to throw out, sort of motivated by thinking about this, a proposal for what observables should be in de Sitter space. And it goes like the following. So if you have a bulk operator in de Sitter space, it can be evolved up to scribe plus using its equation of motion. And this kind of thing was done in ADS by these people who wrote bulk operators in terms of boundary operators. But in Vasilyev gravity, it's particularly simple. The operator at a point here becomes a Wilson surface operator of operators in the dual conformal field theory. And in fact, de Sitter space can be thought of as the space of a certain kind of sphere, geodesic spheres in scribe plus. And the reason, well, one way to see that that's true is that you take any point in de Sitter space and follow its light cone, and that gives you a unique oriented two-sphere up in scribe plus. So we can simply identify that space of two spheres with de Sitter space, and this is a natural thing to do, because from the point of view of the boundary field theory, you should talk only about things that live on the boundary. Now, physical correlation functions, or a set of observables in de Sitter space, a natural thing to think about perturbatively is the set of correlators that all live in the same causal diamond. So if we consider correlation functions between points just in this diamond here, those can be measured by experiments that whose results can be relayed to one another. We cannot relay the result of an experiment here to the result of an experiment here. So on the other hand, points in the causal diamond, in the southern causal diamond, are related to spheres in scribe plus, these geodesic spheres with one orientation. In other words, they're related to geodesic spheres which divide the North Pole and the South Pole. So the proposal is that the physical observables in this context in DSC FD should be the set of Wilson surface operators that live on these two spheres that are the intersection of light cones of points with scribe plus, and it should only be those ones that divide the North and the South Pole. And the good point of this is, unlike bulk observables, which are not, we can't have bulk observables in quantum gravity because once the metric starts to fluctuate, the points move around and we no longer know what we mean by the correlation function at 2 points. So that's why we're forced to talk about boundary observables. So the good point about these observables is that they're mathematically well defined and coordinate invariant, and also at weak coupling, they reduce to what we would naturally call a good set of observables in perturbative quantum gravity in de Sitter space. And so in conclusion, there's a lot of things, the conclusion is that there's a lot to do. We want to complete the DSC FD dictionary in the way that we spent 5 years doing for the ADS CFT dictionary. There are many things we don't understand. We'd like to study things like adding relevant operators and understanding what a Big Bang is. There are more Vasiliev theories. Here I've talked only about one of them. What are their duals? We'd like to do it in different dimensions. We'd like to understand the de Sitter entropy. And maybe we can even embed it in string theory. Recently there's been a lot of progress in understanding how the Lorentzian versions arise in some limit of ABJ theories, and maybe some modification of that will lead us to a de Sitter embedding in string theory. I'll stop there.
So it seems a little bit surprising that the correspondence between de Sitter space and anti-de Sitter space is so non-trivial. I mean, from naive point of view.
So non-trivial?
Yes, because you see basically the difference between de Sitter space and anti-de Sitter space is the sign of the curvature. So naively, I would expect that if I just change the sign of the curvature, things should be almost the same. But you were saying that the things are so non-trivial, like Big Bang corresponds to mass gap, the renormalization group flow corresponds to the influence.
That's one of the things that's fun about. First of all, let me say that going from anti-de Sitter space to de Sitter space was not trivial in string theory, and we haven't succeeded in doing it in a simple way. Chris Hull wrote a paper many years ago just trying to do an analytic continuation, and you find that it becomes unstable and you have imaginary fluxes and so on. It is mathematically trivial in higher spin gravity to go from anti-de Sitter space to de Sitter space, but conceptually, that's one of the wonderful things about it, is mathematically it looks very trivial, but conceptually it's extremely confusing. We don't understand what observables are. We don't understand what the entropy is. We don't understand what happened to unitarity. We don't understand how time could have a beginning. So it's a wonderful laboratory where the mathematics is in control, but the physics is very hard to understand.
So I've asked you this question before, but maybe there's been progress. As I understand it, on the gravity side, there's a scalar field whose potential it is that you're talking about when you discuss the cosmological constant. What is the shape of that potential? Do you know if it's stable or metastable?
I don't know much about that potential. No.
So we're not sure if this is a stable or metastable realization of de Sitter space.
We're not sure if it's stable or metastable, and we're also not sure what stable or metastable means.
Well, I think we might hear more about it in Dan Harlow's talk, but I was wondering if just in the Vasiliev theory, what's known about the scalar potential?
We don't know it.
Two brief comments on it. on this subject. It seems to me that you don't have to go very far to find examples of DSC FD, because indeed, if you simply make analytic continuation in Yang-Mills, let's take n equals 4, Yang-Mills theory, which is the dual of ADS, and do analytic continuation.
Yes.
What we will get is the Yang-Mills theory at complex coupling constant, which is, in principle, it's some non-unitary conformal field theory.
Yes.
Now, as you said, it might be very confusing, complex fluxes, etc.
Right.
However, there are arguments to show that non-unitary conformal field theories, which we encountered in 2 dimensions many times, actually, they are describing unstable vacua. So it's simply the fact that you deal with the non-unitary conformal field theory, which is dual to DS, I think may simply mean that there is no stable DS, that DS is decaying. So that's basically what I wanted to say. It's a bit non-trivial to see that when you have negative probability in non-unitary conformal field theory, how to interpret this negative probability or probability greater than 1. Negative probability means simply that the floor goes off under you. The system decays. When you have it describes metastable state.
Of course, it might be that there's a consistent theory for observers within a static patch, and de Sitter space could still be unstable. So an observer in a static patch may or may not be able to observe such an instability. Now, what's different about the Yang-Mills case, so there is not a stable theory in it, even in a static patch, right? Because if you just take imaginary coupling constant in the Yang-Mills theory, you immediately have propagating degrees of freedom with negative norm.
In the case, you always have negative probabilities, but that's a good thing to derive. It's very nice to have negative probabilities.
Okay, last question.
Well, I'm not sure if it's a question or a comment, I guess a question. You mentioned 2 problems and they seem to be closely related. One is that your graphic dimension is the time, so you map a renormalization group into a time evolution, and all of a sudden time evolution isn't unitary. On the other hand, you have devil's time getting your theory unitary. Well, maybe it isn't.
Well, I mean, the problem with that is, we live in de Sitter space. We may well live in an asymptotically de Sitter space, and there's something that that we call unitarity, which is experimentally verified to extraordinary accuracy. So if you have a theory in which unitarity is not an exact symmetry from the very beginning, it's incumbent on you to explain how physics is unitary to such an extraordinary good approximation.
Well, the world seems unitary because asymptotic Hubble expansion time is so slow, especially compared to your quantum experiments. If you somehow, in fact, we have no idea if our world is unitary on a Hubble time. We know it's unitary on a time scale of 10 to the minus 20-something seconds. Maybe with superconducting experiments on a schedule of seconds, certainly not on the Hubble time. And that's where the fact that our space is not flat comes in, which mean all kinds of de Sitter properties go away if you go curvature. If radius of curvature goes to infinity, presumably it's also true in de Sitter.